For as long as humanity has gazed upon the night sky, the moon has held a place of profound mystery and intrigue. Civilizations throughout history have woven myths and legends around our celestial neighbor, imbuing it with symbolic significance. And in the modern age, the moon continues to captivate our imaginations, inspiring both scientific exploration and a healthy dose of speculation. But what if the whispers of something truly extraordinary happening on the moon weren't just speculation? What if there was credible evidence pointing toward ongoing anomalies, hidden activities, and unexplained phenomena? That's exactly the bombshell that a NASA insider has just dropped, setting the scientific community and conspiracy theorists alike into a frenzy. According to this individual, who for obvious reasons must remain anonymous, the moon is not the desolate, inactive rock we've been led to believe. Instead, it's a place of dynamic activity, harboring secrets that challenge our fundamental understanding of the cosmos. Now, before you dismiss this as another outlandish conspiracy theory, let me assure you that we're going to approach this with a critical and objective eye. We're not here to blindly accept claims without evidence. Instead, we'll delve into the available scientific data, examine the anomalies that have baffled researchers for years, and explore the potential implications of these startling revelations. So, what exactly did this NASA insider reveal? Well, the claims are multifaceted, ranging from unexplained lunar structures to unusual energy signatures detected on the far side of the moon. Perhaps most intriguing, the insider alleges that there's evidence of ongoing geological activity, including recent seismic events and potential volcanic eruptions far more recent than previously thought. And they're going to go into specifics. They claim that these events, if true, would rewrite lunar history and force us to reconsider the very nature of our nearest celestial neighbor. The insider also points to anomalies in the lunar gravitational field, discovered by missions like GRAIL, Gravity Recovery and Interior Laboratory, as potential indicators of hidden subsurface structures or unusual density variations. These anomalies, they suggest, could be evidence of ancient lunar bases, either natural or artificial, buried beneath the surface. Of course, these are extraordinary claims, and they require extraordinary evidence. But what makes this insider's revelation so compelling is the fact that they align with a growing body of scientific observations and unexplained phenomena that have puzzled researchers for decades. Think about it. The moon, for years, was dismissed as a geologically dead relic, a relic of the solar system. Yet, recent missions have revealed that's not the case. From unexpected seismic activity to tantalizing hints of water ice in permanently shadowed craters, the moon has proven to be far more complex and dynamic than we ever imagined. The insider's claims add another layer of intrigue to this already fascinating picture, suggesting that there's far more to the moon than meets the eye. But how much of this is grounded in reality and how much is simply wishful thinking? That's what we're here to find out. Throughout this video, we'll dissect the insider's claims, compare them with existing scientific data, and explore the potential implications of these startling revelations. We'll examine the anomalies that have baffled researchers for years, from the mysterious lunar swirls to the unexplained flashes of light observed on the lunar surface. We'll also delve into the scientific evidence suggesting that the moon's interior may be far more active than previously thought, including the discovery of deep moonquakes and the potential for ongoing volcanic activity. And we'll explore the possibility that these phenomena could be linked to hidden subsurface structures or unusual density variations, as suggested by the NASA insider. But above all, we'll approach this with a healthy dose of skepticism and a commitment to uncovering the truth, no matter where it leads. Because whether these revelations turn out to be groundbreaking discoveries or elaborate fabrications, one thing is certain: the moon continues to hold a powerful grip on our imaginations, reminding us of the vastness and mystery of the universe that surrounds us. So, buckle up, because we're about to embark on a journey to the dark side of the moon, to uncover the truth behind these startling claims and explore the weird things that may be happening on our celestial neighbor right now. Are you ready? Let's get started. For as long as humans have looked skyward, the moon has been both a familiar companion and an enigma. From ancient myths that saw it as a divine being to modern conspiracy theories that cast it as a site of hidden alien activity, our celestial neighbor has never ceased to provoke wonder and speculation. Yet behind the sensational claims lies a far more compelling story. No, this is not a myth or a legend. It is very well seated in hard science, patient exploration, and revolutionary discoveries. A NASA insider has just revealed that weird things are happening on the moon right now. So, what is the truth behind all of this speculation? Today we'll answer all of this. Let's dive into the fascinating world of lunar anomalies, shall we? We're talking scientific evidence and weird occurrences that might just make you question everything you thought you knew about our silent satellite. Get ready, because this is going to be mind-blowing. First up, the Grail mission. In September 2011, NASA launched the Gravity Recovery and Interior Laboratory, better known as the Grail mission. Unlike other lunar missions that focused on surface exploration or sampling, Grail was designed to probe the moon's hidden interior by mapping its gravitational field with unprecedented precision. The two nearly identical spacecraft flew in tandem, maintaining a controlled formation while measuring minute changes in the distance between them caused by subtle variations in the moon's gravity. These changes, on the scale of microns, provided scientists with a way to see beneath the lunar crust and examine density differences in the subsurface that no camera or lander could reveal. And the results? Paradigm shifting. Grail confirmed that the moon's crust is thinner than previously thought. Earlier models had suggested crustal thicknesses of up to 60 kilometers. But Grail's data showed that in many regions, the crust is closer to 34 to 43 kilometers thick. This had profound implications for theories of lunar origin, implying that the moon's early history of magma ocean crystallization and differentiation was more complex than we thought. But it gets weirder. Grail's gravity maps also revealed a surprising level of structural asymmetry between the lunar near side and far side. The side facing Earth showed evidence of large gravitational anomalies linked to ancient volcanic activity and concentrations of heat-producing radioactive elements in the mantle. By contrast, the far side displayed a more uniform but rugged gravitational landscape. This asymmetry helped explain why volcanic eruptions were far more common on the near side while the far side remained geologically quiet. Scientists demonstrated that the near side mantle is more deformable under Earth's gravitational pull than the far side mantle. This confirmed that the two hemispheres of the moon are not only geologically distinct on the surface, but also fundamentally different deep inside. The likely cause? An uneven distribution of radioactive isotopes, such as thorium and potassium, which continue to produce residual heat billions of years after the moon's formation. Another important contribution of Grail was its ability to trace the origins of lunar basins and impact structures. The mission revealed that many large basins, including the Imbrium and Orientale, have ringed structures extending deeper into the crust than previously realized. These gravity signatures suggested that the moon's crust and mantle responded elastically to colossal impacts, and that these events shaped the moon's geological evolution more profoundly than surface imaging alone could show. Now let's talk about lunar flexing. You heard that right, the moon flexes. It was assumed that the moon was shaped primarily by ancient impacts and volcanism billions of years ago. Yet recent analyses of lunar data, especially from NASA's Grail mission, have revealed that the moon is still undergoing a subtle but measurable process known as tidal deformation. This phenomenon is caused by Earth's gravity, which exerts a constant pull on the moon. The gravitational interaction stretches the moon slightly, producing a bulge aligned roughly toward Earth. Spacecraft equipped with high-precision instruments have shown that the deformation leaves a measurable imprint on the moon's gravitational field. And guess what? The near side is noticeably more deformable than the far side. This suggested that the two hemispheres of the moon are also distinct deep within their interiors. The difference in flexing can be explained by variations in the internal composition of the lunar mantle. Geological evidence and chemical mapping had already shown that the near-side crust contains higher concentrations of radioactive elements such as potassium, thorium, and uranium, collectively referred to as creep. Park's analysis of Grail's tidal deformation data confirmed that the near-side mantle remains warmer than the far-side mantle. The warmer interior allows the near side to deform more easily under Earth's gravitational influence, while the cooler far-side mantle retains greater rigidity. This asymmetry helps explain why the moon looks the way it does. Let's get to lunar secrets. For much of the 20th century, the moon was regarded as a fossilized remnant of the early solar system whose most active days had ended billions of years ago. However, more recent missions and analyses have upended this view, showing that the moon is not the dead body it was once believed to be. Instead, its interior still bears subtle signs of activity, and its surface preserves clues that continue to reshape our understanding of planetary evolution. One of the most persistent mysteries involves the occurrence of deep moonquakes. Detected by seismometers placed on the lunar surface during NASA's Apollo missions, these quakes occur hundreds of kilometers beneath the crust, far deeper than typical tectonic earthquakes on Earth. Unlike the shallow moonquakes, which are often tied to tidal stresses from Earth's gravitational pull, deep moonquakes recur in clusters and are thought to be linked to localized zones of partial melting within the mantle. This suggests that the moon's interior retains residual heat, especially beneath regions enriched in radioactive elements. But wait, there's more. The discovery of relatively recent volcanic activity has been another surprise. In December 2020, China's Chang'e 5 mission successfully returned lunar samples from Oceanus Procellarum. Radiometric dating of these basalts revealed that they crystallized as recently as 120 million years ago. This date is staggeringly young compared to the widely held view that lunar volcanism ceased about 1 billion years ago. The presence of such young volcanic deposits implies that the moon retained sufficient heat to generate magma long after most scientists thought it had gone cold. Researchers propose that high concentrations of heat-producing elements, combined with localized mantle anomalies, allowed volcanism to persist in isolated regions. If confirmed by further missions, this would make our moon one of the most enduringly active small bodies in the solar system. Central to understanding both deep moonquakes and late-stage volcanism is the distribution of creep. You see, potassium, rare earth elements, and phosphorus are byproducts of the final stages of magma ocean crystallization. Because they are incompatible with early crystallizing minerals, they became concentrated in the last pockets of molten material. The fact that creep is concentrated almost entirely on the moon's near side raises fundamental questions about the events that shaped lunar formation. Some models suggest that Earth's gravity may have influenced the distribution of heat-producing materials, while others propose that a colossal impact during the moon's early history created an asymmetric mantle. And finally, the moon's unusual composition also makes it an attractive site for resource exploration. The near-side's volcanic plains contain rich deposits of titanium and iron, which could be used in future colonization efforts on the lunar surface. Silicon, another essential material for electronics and infrastructure, is found in abundance in the lunar regolith. Beyond these familiar resources, the moon offers helium-3, a rare isotope deposited by the solar wind. Because helium-3 is scarce on Earth, but potentially useful as a fuel for future nuclear fusion reactors, its presence on the moon has drawn attention as a long-term energy source. Artemis, officially announced in 2017 and accelerated under subsequent administrations, represents NASA's most ambitious attempt since Apollo to establish a sustained human presence on the moon. But unlike Apollo, which was driven by Cold War competition and focused on short-duration missions, Artemis is about building infrastructure, conducting in-depth scientific research, and preparing for even deeper space exploration. The long-term vision is nothing short of lunar colonization by the 2030s. This isn't just a U.S. effort. Artemis involves crucial international partners like the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. And just as importantly, it's leveraging the power of private industry through contracts with companies like SpaceX, with their Starship lunar lander, and Blue Origin, developing the Blue Moon system. This collaboration is key to making lunar exploration sustainable and affordable. But what does all this have to do with those weird things we've been talking about? Well, discoveries from missions like Grail and Chang'e 5 are directly influencing how Artemis is being designed and executed. That incredibly detailed gravitational mapping we discussed, it's not just about pure science. It's improving the precision of landing systems, allowing spacecraft to target those scientifically rich and potentially resource-heavy areas, like the lunar South Pole. Artemis III, currently scheduled for as early as 2026, aims to land astronauts in this very region. Why the South Pole? Because it's believed to contain vast deposits of water ice trapped in those permanently shadowed craters. This isn't just a cool scientific find. It's a game changer. Water ice is an essential resource, not only for sustaining human life with drinking water and breathable air, but also for producing rocket fuel through the electrolysis of hydrogen and oxygen. Imagine fueling future missions directly from lunar resources. That's the power of in situ resource utilization, and it doesn't stop there. The accurate knowledge of the moon's internal asymmetry and crustal density variations, revealed by Grail, is also informing seismic monitoring. This is crucial to ensuring that habitats and infrastructure are placed in geologically stable zones, minimizing the risk of damage from moonquakes. You don't want to build your lunar base on top of an active seismic zone, right? Those findings about residual heat and localized mantle activity are also influencing colonization strategies. The areas enriched in creep elements and thorium, concentrated on the near side as we discussed, point to regions with distinct thermal histories. The volcanic plains on the near side provide smoother landing zones and potentially easier access to resources like titanium and iron, vital for construction and manufacturing. Understanding the moon's geologic two-faced nature helps mission planners balance scientific priorities with the practical needs for building materials, radiation shielding, and energy production. Speaking of energy production, the possibility of harnessing helium-3, a rare isotope deposited in lunar regolith by the solar wind, is being taken more seriously. Helium-3 is scarce on Earth, but could potentially serve as a clean and abundant fuel for future nuclear fusion reactors. If we can figure out how to extract and utilize it efficiently, the moon could become a significant energy hub for both Earth and beyond. But remember, helium-3 isn't evenly distributed. Concentrations are higher in the regolith of the lunar highlands than in the mare basalts. Mapping and quantifying these deposits through future orbital missions and landers will be crucial for planning sustainable lunar settlements. Artemis isn't just about getting back to the moon. It's about establishing the technologies and infrastructure that will enable permanent habitation. Think modular bases, like the proposed Artemis Base Camp. These will include habitats specifically designed to withstand the harsh lunar environment, intense radiation, regolith storms, and extreme temperature fluctuations ranging from a scorching 120 degrees Celsius in sunlight to a bone-chilling minus 170 degrees Celsius in shadow. Power systems, including large-scale solar farms and even small, portable nuclear reactors like NASA's Kilopower, are being planned with that resource mapping in mind. The goal is to ensure that settlements are placed in areas that offer both ample sunlight for solar power and easy access to subsurface volatiles like water ice. The lessons learned from Grail and other geophysical surveys are proving crucial for identifying structurally sound regolith layers suitable for tunneling or even 3D printing habitats directly from local materials. Imagine constructing a lunar base using lunar dirt. Ultimately, every single insight we gain about lunar flexing, residual volcanism, or crustal asymmetry contributes to a broader understanding of how small bodies retain heat, sustain activity, and evolve over billions of years. These models aren't just relevant to the moon, they're directly applicable to understanding Mars's volcanic past, Mercury's crustal dichotomy, and even the thermal dynamics of tidally locked exoplanets orbiting distant stars. The moon, in this context, becomes more than just a destination. It becomes a stepping stone, guiding humanity toward a far broader cosmic understanding. It's a testbed for technologies and strategies that will ultimately allow us to explore and colonize other worlds.